This video covers several aspects of a general chemistry first-order integrated rate law problem. The decomposition of SO₂Cl₂ results in a linear plot where the natural log of SO₂Cl₂ versus time has a slope of negative 1.8 times 10 to the negative 5 inverse seconds at a specific temperature, where the chemical equation is shown as SO₂Cl₂ yielding SO2 plus Cl2. Our first step will be to search this statement for clues about this reaction. Our first clue is that there's a linear plot with the natural log of SO2Cl2 concentration versus time. That linear plot tells us that the reaction must be first order in SO2Cl2. The second clue is that linear plot has a slope of negative 1.8 times 10 to the negative 5 inverse seconds. We know that the rate constant, K, is equal to the absolute value of this slope. Therefore, the rate constant for this reaction is 1.8 times 10 to the negative 5 inverse seconds. Our third and final clue is that the units of K and the units of slope indicate that this reaction is first order in SO2Cl2, since the units are inverse seconds. So in summary, before we solve any problems, we first search the statement for clues. We find the reaction is first order in SO2Cl2, and we find the rate constant is 1.8 times 10 to the negative 5 inverse seconds. The first problem we'll solve here is to write the rate law for this reaction. Since the reaction is first order in SO2Cl2, and that's the only reactant, the rate law then is rate equals K times the concentration of SO2Cl2 to the first power, or simply K times SO2Cl2. You may also see a rate law written with K, the rate constant, numeric. In that case, it would be rate equals 1.8 times 10 to the negative 5 inverse seconds times SO2Cl2 concentration. The next problem is to calculate the half-life for this reaction. Since this is a first order reaction, our half-life is simply 0.693 divided by K, the rate constant. Notice that the half-life of this first-order reaction is independent of initial concentration of reactant. In contrast, the zero-order and second-order half-lives are dependent on initial concentration. We plug in our rate constant, and we find that our half-life is 38,500 seconds, or correctly rounded to two significant digits, 39,000 seconds. Third problem asks, how long will it take for SO2Cl2 to decrease to 25% of its original concentration? The key step needed to solve this problem is to recognize that the SO2Cl2 concentration at time t, which we don't know yet, is equal to 25%, or 0.25 times the initial concentration of SO2Cl2. We'll use the integrated rate law for a first-order reaction, as shown here, and simplified with A representing SO2Cl2. We need to rearrange this equation to solve for T. To do that, we'll first put both natural log terms on the same side, and then we'll recognize that T is equal to negative 1 over K times the natural log of our reactant concentration at time t divided by our initial reactant concentration. That means for this problem, T is equal to negative 1 over K times the natural log of SO2Cl2 at time t divided by the concentration of SO2Cl2 initially. Using that key step shown above, we can reduce this to time equals negative 1 over K times natural log of 0.25 SO2Cl2 initial divided by SO2Cl2 initial. Those initial concentrations of SO₂Cl₂ will cancel, and we'll plug in our rate constant, and we'll find that -1 divided by the rate constant times the natural log of 0.25 gives us a total of 77,000 seconds. The fourth problem we'll solve is to determine how long it will take for the SO₂Cl₂ concentration to decrease from 0.054 to 0.052 molarity. We'll use the first order integrated rate law, again solved for t as we did in the previous problem, and we'll plug in the concentrations for SO₂Cl₂ both at time t and at time 0 initial. When we do that and include our rate constant, we find that our time for the SO₂Cl₂ to decrease to 0.052 molarity is 2,100 seconds, again correctly rounded to 2 significant digits. The next problem states if SO₂Cl₂ concentration starts at 0.0105 molarity, what concentration of SO₂Cl₂ remains after 2.0 hours? We again return to the integrated rate law equation for a first order reaction, and we insert our rate constant and our time and our initial SO₂Cl₂ concentration. When we do this, we find that the natural log of our SO₂Cl₂ concentration at time t, which is 2 hours, is equal to -4.686. That's not my final concentration. In order to do that, I need to remove the natural log, and I find that my SO₂Cl₂ concentration after 2 hours is 0.0092 molarity. Our sixth and final problem is if SO₂Cl₂ concentration starts at 0.0105 molarity, what concentration of SO2 is present after 2 hours, assuming the reaction vessel started with no products? We recognize that our SO₂Cl₂ concentration at time equals 2 hours is equal to 0.00922 molarity as calculated in the previous step. I've added 1 digit beyond the 2 significant digits in order to prevent a rounding error in this calculation. I now recognize that the SO₂Cl₂ concentration that has been consumed over the course of 2 hours of reaction is equal to the initial concentration minus the concentration at 2 hours. When I plug in the initial concentration and subtract the concentration at 2 hours, I find that the quantity of SO₂Cl₂ consumed is 0.00128 molarity. Therefore, since in the original chemical equation, 1 mole of SO₂Cl₂ consumed creates 1 mole of SO2 product, then the concentration of SO2 product is equal to the concentration of SO₂Cl₂ that was consumed over this course of 2 hours, and therefore the concentration of SO2 that's produced is 0.00128 molarity SO2.